analysis. I don't know if you can all hear me.
Yes, we can get you. So.
I can hear you. I can hear you.
Okay, that's okay. Yeah.
Can
Should
you
I
guys
go
see?
on?
Yeah. Can everyone see the screen sharing? Can you see? Yes, we can go on, I think. If everyone can see the screen, it's okay.
We have more participants, so yeah, I'll go on. So first slide.
Okay, let's go.
So there are a number of analyses that can be done on drinking water. I'll be handling today physical parameters. I'll be handling testing for physical, chemical, microbial, and heavy metal analysis. For this analysis, a variety of techniques can be used. That is the calorimetric, potentiometric, turbidimetric, volumetric, titrimetric. I think we remember this one from our maybe our high school education. Photometric and gravimetric. Next slide. Yeah, so physical analysis. For this, I'll be taking you through the following parameters. That is pH, color, turbidity, temperature, solids, and conductivity. And then after conducting your test, you usually compare your results to the regulatory body that regulates, pardon? Yeah, after conducting your analysis, you usually compare your results with the maybe WHO standards and the regulatory body in your country. For example, here in Kenya, we have the Kenya Bureau of Standards that provides standards for drinking water. Next. We'll start with color. So color is detectable to the eye when it exceeds 5 Hz. So for starters, the unit for measuring color is called Hz. And the color of water is analyzed using the calorimetric method. For this, you need the following equipment: comparator, a color disc, and a color viewing tubes. If you can scroll to slide number 7, we can see what we mean. Slide number 7. Yeah, so on your left, you have the color disc. The color disc, the color disc contains ranges. You can have from 0 to 30 or from 30 to 70. So when you're conducting your analysis, you always start from the low range disc, and then the high range disc is from 30 to 70. And then on the right, you have your comparator and the tubes that are inside of the color viewing tubes. So back up. So the procedure for that is as follows. You have 2 color tubes. So one of the color viewing tubes is filled to the mark with the water sample to be tested. And then you're going to stopper each, that is put the cap to the color viewing tube. That is what I mean by stoppering it in such a way that all air bubbles that might be present in the color viewing tubes are excluded. And then you are going to insert that color viewing tube with the water sample to be tested into the right opening of the comparator. And then the other color viewing tube is filled with distilled water to the mark and then stoppered in the same way, just to ensure that there are no air bubbles in the tube, and then inserted in the left opening of the comparator. And then the color disc is inserted into the comparator, always beginning with the low range color disc, that is from 0 to 30. And next. And then you're supposed to hold the comparator up against a light source. So if you're in the lab, you can just go maybe to a window and you hold the comparator up. And then you rotate the color disc until the color of the liquid 2 tubes. That is the tube with the distilled water and the tube with the water sample to be tested are, as viewed through the opening in the comparator, are identical. And then if no color match is obtained by using maybe the low color range, you're going to change to the higher color range. And then the reading obtained is the apparent color of the water. And then who provides a maximum of 15 hazens for drinking water. Yeah, can move on to the next. Is there a question so far? I will assume no. Okay. The next test, the next parameter we're going to test for is turbidity. So turbidity is the optical effect caused by the dispersion of and interference with light rays passing through water containing small particles in suspension. So basically, you're going to pass light through your water sample to just see how much the particles in a water sample interfere with the light passing through the sample. And then for this, we use the turbidimetric method of analysis. And the unit for measurement is called the NTU, that is the nephelometric turbidity unit. And then the apparatus for this will include the turbidimeter, a glass cell, and a Martin cloth. If we go to slide, is it 7? Slide 10, you can see that. Yeah, so on the left, you have the turbidimeter, and then on the right, you have your, yeah, the turbidimeter with a glass cell. And then a Martin cloth is basically just a cloth, any cloth, you can go with cotton, that you're going to use to wipe the glass cell with, just to get the right measurements. You basically use this cloth to wipe off any water on the glass tubes. So back the slide before that. Yeah, so the procedure for this analysis is as follows. You are supposed to check the glass cell and rinse it 3 times with distilled water. This is common for all water tests that you'll be conducting in the lab. The apparatus you have, you're always supposed to rinse them 3 times with distilled water. And then you take the sample of water that you have, you shake it. This is another thing that we should always practice. The sample, before you test any sample for anything, you're always supposed to shake it, just to ensure that the sample you have has a uniform distribution of maybe particles in the water. So you shake the sample of water that you have, and then you pour it into the glass cell to the mark. So the glass cell has a mark. Mostly it usually goes to around 10 ml. So you fill water to that mark, and then you wipe its exterior using a Martin cloth. The cloth I just described could be cotton, could be whatever fabric that is that absorbs water well. And then you put the glass cell with the water sample into the turbidimeter, switch it on, and then take the reading. Who recommends a maximum of 5 for drinking water? Any question, Tilda? We are good? You can say something. Okay, I'll move on to pH. If I'm too fast, you can just tell me to slow down a bit, or you can ask questions as we go along. We're going to move on to pH. And we know that pH is the alkalinity or acidity of a substance. The pH scale, as we all know from our primary or high school, measures scale ranges from 0 to 14. 0, and then 7 for neutral. So values ranging from 0 to 4 are highly acidic, and then from 4 to 7 are slightly acidic, and then 7 neutral, 7 to around 10, that is slightly basic, and then 10 to 14, highly basic. So high pH causes a beta test in water, buildup and blockage in pipes, and itchy dry skin, while low pH causes the corrosion of pipes. Both the potentiometric and calorimetric methods can be used for this analysis. The calorimetric method is the one that uses the comparator, the one that I just showed you before. Apparatus used for the calorimetric method is the same one as the one used for color. So we'll start with that one. So the procedure for that is as follows. 2 test tubes are rinsed with distilled water, as said before, and then you shake the water sample, and then you pour 10 ml into the test tube, and then one of the test tube is placed onto the left opening of the comparator, while and then you add 0.5 ml of indicator into the other test tube, and then placed into the right opening. And then a color disc comparative to the indicator is inserted into the comparator. So for this test, different color discs are available depending on the indicator you're going to use. If you're using phenolphthalein, there's a color disc range for that. And then so after that, after putting the tubes into the comparator, you're going to insert the color disc into the comparator. And then as with the test for color before, you're going to hold the comparator up against light and then rotating it until you get until the color as viewed through the opening of the comparator of the two tubes is similar, and then you're going to take your reading. And then a pH scale of 6 to 5 to 8.5 is the WHO recommended standard for drinking water. I'll move on to the potentiometric method of pH analysis. Yeah, so for this one, we're going to need a move on to the next. Yeah, for this one, you're going to have for this one, you might have, you can get the multimeter. I think on the right end, you have the multimeter with electrodes and basically electrodes and a clamp just to hold the electrodes together. So as usual, you're going to take your water sample, shake it, and then pour it halfway into the beaker, and then rinse the electrodes using distilled water and immerse them into the sample for analysis. Switch on the multimeter and then take the pH reading. With this one, you can obtain the pH reading, the conductivity readings, and the temperature readings. As I mentioned earlier, a pH scale of 6 to 5 to 8.5 is the WHO recommended standard for drinking water. What you have on there is a pH meter and a potentiometer. Multimeter, sorry. We can move on to the next. Temperature. So temperature is the hotness or coldness of something. So the temperature of drinking water is dependent on the temperature of the air around it. If you want to drink cold water, you'll obviously put it inside the fridge. If you want to drink room temperature water, you'll just leave it to the room, and then you can drink room temperature water. If you want to drink hot water, you can always heat up your water. So that is to say that the temperature of drinking water is dependent on the temperature of the air around it. So temperature can be analyzed using the potentiometric method, as you had said before, shaking the sample, putting it into the beaker, and then inserting the electrodes into the beaker, and then switching on the multimeter, and then getting the readings as you had done for the pH. And then, so the procedure to be followed is the same as that for the pH method. The SI unit for temperature, as we all know, is degrees Celsius. So basically, temperature maybe affects the taste of the consumer. Sometimes the consumer wants cold water, so the consumer can regulate the temperature of the water they want. There's really no set temperature for drinking water as per the WHO regulations. You can drink whatever temperature of water you want. We'll move on to electrical conductivity. Yeah, so conductivity is the measure of the ability of water to pass an electric current. We know that current is basically a flow of electrons. So water has oxygen and hydrogen ions, which means that it will allow a current to pass through it. But distilled water won't allow current to pass through it because it does not have ions, other ions, say sodium ions or magnesium ions that allow normal water to allow electricity to flow through it. So conductivity in water increases as salinity increases. That is because saline water, could be water from the ocean, has more ions as compared to drinking water. Yeah. So the potentiometric method of analysis is used for the parameter, and the procedure for temperature is followed. So as you had done before, as you get your pH readings, you can get your temperature readings as well. and you can get your conductivity readings. So conductivity is measured in microsiemens per centimeters, and WHO recommends a maximum of 2,500 microsiemens per centimeter. That is conductivity for drinking water. What you have here is almost the same thing as you had before. So with this equipment, you can just get the reading directly from the sample you have. Any question? I can take a question or two. I guess you're all okay. So oxidation reduction potential. ORP is measured to determine the oxidizing or reducing potential of a water sample. It is a measure of the water's ability to either oxidize or reduce another substance, and it is measured by the electrodes of an ORP meter. So with this one as well, you have a meter already, so you can just get the readings immediately from inserting the electrodes into a sample. A positive reading on an ORP meter means that the substance is an oxidizing agent, while a negative reading indicates that the substance is a reducing agent. Continuation. Yeah. So ORP indicates how sanitized or contaminated your water is based on its oxidation and reducing properties. In order to be safe to consume, recycle, or come into contact with our skin, water is treated with a sanitizing agent to have a higher oxidation potential, producing a higher ORP reading. And by routinely monitoring the ORP levels, it's possible for you to monitor the effectiveness of a sanitizing agent or adjust the water treatment plan accordingly. So according to the WHO regulations provided, and when you use the ORP meter to measure the oxidation and reducing potential of your water, anything above 600 MV is a good ORP reading. What you have there, next slide. Yeah, you have the ORP meter there. With this test, you can just get your readings directly. We can move on to chemical analysis. Chemical analysis. So we have just covered physical analysis, and we are looking at basically with physical analysis, these are things that you can see, things that you can observe, things that you can smell. You can maybe smell the scent of your water to determine whether this water is good for drinking. You can see the color of your water and maybe get to tell whether it's good for drinking. Now we are going to tackle chemical analysis. We are basically testing for the chemicals that might be present in your drinking water. So the chemical analysis of water is carried out to determine the presence and levels of different chemical components in water. And parameters analyzed include alkalinity, calcium ions, magnesium ion, total hardness, chloride, fluoride, nitrates, CO2 ion, and many others. For this analysis, we'll use the photometric and the tachymetric or volumetric analysis methods. Yeah, and on to the next slide. So the next slide, yeah, we'll start with alkalinity. Alkalinity is the measure of the ability of a water body to neutralize acids and bases, thus maintaining a fairly stable pH. It is basically the buffering capacity of a water body. So what we're trying to see is whether we can be able to add any acid or bases, any acid or base to our water without interfering with its ability to, carry on with its activities. So, but basically here we look at maybe waters in the lakes or oceans or rivers or whatever, just so that we can see what amount of maybe not really pollutants or contaminants, what amount of discharge you can do to a river, just enough to ensure that we don't contaminate the water, just enough to ensure that the water is still, the organisms in the water can still survive. So that is what it means by the measure of the ability of the water body to neutralize acids and bases, but at the same time, maintaining a fairly stable pH. So alkalinity is dependent on the presence of carbonates, hydrogen carbonates, and hydroxides. Water with a high alkalinity will experience little change, as say when an acid is added into it. Next slide. Alkalinity is important to the health of the body. Organisms living therein need to stay in a fairly stable aquatic environment. If you introduce a shock to maybe water body, say you add acids into the water, obviously the organisms within will, suffer because you are disrupting their usual, way of life. Whatever conditions they're used to surviving in, you are altering that. The alkalinity of surface water comes from the rocks and land surrounding that water body. That is, when it rains, the runoff washes over rocks and goes into the river. So this is what affects the alkalinity of a water body. For this analysis, we use the titrimetric method. Next. So we're going to need a burette stand, measuring cylinder, conical flask, magnetic stirrer, magnetic rod, magnetic stand, and a funnel. And then the reagents for that, we'll use methyl orange indicator solution, phenolphthalein, and sulfuric acid. Next. The procedure for that is as follows. As usual, we always start with rinsing our apparatus with distilled water 3 times. And then we rinse literally everything. You rinse your burette, rinse your any equipment, any glass equipment that you will be using, you need to rinse it with distilled water. So after rinsing that, you're supposed to pour sulfuric acid into the burette. And then you take 50 milliliters, measure out 50 ml of the sample using the measuring cylinder that you have, then pour it into the conical flask. And the conical flask, as you all know, has the magnetic stirrer inside. And then you place the magnetic stirrer on the conical flask with the stirrer onto the stand, and then switching it on. That way it keeps rotating so that just for even distribution of, it's like shaking the sample. So in this case, we won't need to shake the sample because the stirrer is doing the shaking. So 50 ml of the water into the volumetric flask, and then add 3 drops of phenolphthalein indicator into the conical flask, and then you titrate the sample against sulfuric acid until the pink color just disappears. After that, add 3 drops of methyl orange indicator. You'll observe a yellow color, and then you titrate it against sulfuric acid until an orange color is observed, and then you take the burette reading. When you first pour sulfuric acid into the burette, you're supposed to take your initial reading, and then after you complete the titration, you take the final reading, and then the volume, and then you take the difference, that is the final reading minus the initial reading, and then the volume of acid used, that is the tighter volume, you multiply it by 20 to get the results obtained in the following units, that is milligrams per liter. Next slide. Yes. So the tighter value, that is the volume of acid used, you multiply that by 20, and then the results you get, its units are in milligrams per liter of calcium carbonate. And then, as usual, you compare your results with the standards provided for your country, who recommends a maximum of 500 milligrams per liter of calcium carbonate. So that's it with the alkalinity. Chlorides. So chloride is a naturally occurring element that is common in most natural waters and is most often found as a component of salt, or in some cases in combination with potassium or calcium. Chlorides in water corrode metals and give water a salty taste. Hence the need to test for chlorides in drinking water. For this, we'll use the titrimetric method as with alkalinity before. So the apparatus used, next slide. The apparatus used is the same as for alkalinity. You need your burette, you'll need your magnetic stirrer, magnetic stand, magnetic rod, your conical flask, and your funnel. So, and then in this case, what will change is the reagents. For this, we'll use distilled water silver nitrate solution and potassium chromate indicator. Next. The procedure for that is as follows. So as usual, you rinse your apparatus, and then you pour silver nitrate solution into the burette using the funnel, and then you take the initial burette reading. 50 ml of the sample, you measure that out using the measuring cylinder, the 100 ml measuring cylinder, and then pour it into the conical flask with a stirrer, and then add 1 ml of potassium chromate indicator. The color observed will be yellow. And then you will titrate the sample against silver nitrate solution until a brown color is observed. And then you take the final burette reading. You are supposed to repeat the procedure. Now, instead of using the water sample, use distilled water. And then distilled water, just take distilled water, add the indicator, and then you titrate it and then get the final burette reading. And the unit for chlorides is milligram per liter of chloride. And this is calculated using the formula V1 minus V2. That is the titer value for titer value for sample water minus the titer value for distilled water. We multiply that by the normality of silver nitrate. In this case, the normality was 0.0141. And then multiply that with 35 for 50, that is a standard. And then you divide all that by the sample volume used. In this case, we used 50 ml. As usual, the results obtained are compared with the regulatory standards in one's country. But the WHO standard for this parameter is a maximum of 250 milligrams per liter of chloride.
Okay, thank you. I think we have to have a break now because we have some kind of rushing, and so we have a break and we come back in 5 minutes or 10 to complete the session. And if you have a question, please, I will recommend you write in the chat and then you send your questions and then we can proceed. So see you in 5-10 minutes time. Thank you.
Okay, okay.
Yeah.
So the next chemical parameter that we'll be testing for is free CO2, that is free carbon dioxide. So we all know that carbon dioxide exists freely in nature as a component of air, makes about 0.03% of air, of the total air. So carbon dioxide, which naturally occurs in the atmosphere, dissolves into surface water to form a weak carbonic acid, and this causes a decrease in the pH of water. Carbon dioxide in water causes pipes to corrode, just like all acids do, and forms scale with alkaline water. This practically will use the titrimetric method or also the volumetric method, the one that uses literally the one that we just used before. The apparatus used in this are the same as the ones that we've been using for alkalinity and for chloride. So we'll have our usual measuring cylinder, a conical flask, magnetic stirrer, rod, stand, a funnel, a burette, and a burette stand. The reagents that we'll use for this practical will include 0.02 normality sodium hydroxide solution and a phenolphthalein indicator. And then the procedure will be as follows. As usual, we'll rinse our apparatus 3 times with distilled water. And then you will take your titrant, in this case, sodium hydroxide, and then we'll pour it into the burette and take the initial reading. You can get to 0, just for, you can leave it at whatever level, but you can fill the burette up to 0 just for ease in taking your readings. And then you measure out 50 milliliters of the water sample to be tested. Pour it into the conical flask. Add 5 drops of phenolphthalein indicator. Here, a color change to pink, if observed, will indicate the presence of free CO2 in water. That's because phenolphthalein indicator turns pink in an acid. If the sample mixture remains colorless, a color change to pink indicates absence. Sorry, phenolphthalein indicator is pink. Shows indicator turns the sample pink. If it turns pink, it shows the absence of acid in water. That is basically the absence of free CO2, which combines with water to form a weak carbonic acid. But if the sample mixture remains colorless, that is phenolphthalein is colorless in acid, you will continue with the titration. So you titrate it against sodium hydroxide titrant until a pink color is observed. Until the pink color just discharges. Sorry, I think I should have, yeah. Until a pink color is observed, that is from colorless. If it turns pink, that shows that the sample plus the titrant have reached to a base, because again phenolphthalein indicator is pink in base. Sorry. Yeah, we don't have values for free CO2 in water as recorded by WHO, but basically with free CO2, we just want to see how acidic something of the sort your water is. Again, so the data value gotten as with the parameter, the parameters tested before, you will get your data value and then you multiply it by 20. Yeah. And then moving on to total hardness. Total hardness is the sum of the concentration of calcium and magnesium ions. So the presence of calcium and magnesium in water causes your water sample to be hard. So it is caused by dissolved calcium and magnesium ions, and is formed when water or over limestone or salt areas. Limestone is calcium carbonate, literally CaCO3, and this is what causes the hardness in water. So this practical is done using the trichromatic method, and the apparatus used is the same as the ones used in the previous analysis for the trichromatic analysis. The reagents will be different. We'll use a total hardness solution. Our indicator will be Eriochrome black tea, and our titrant will be standard EDTA titrant 0.01 molarity solution. Next slide. Next slide. Yeah. The procedure is as follows. As usual, we'll take our apparatus, rinse it 3 times with distilled water, and then we'll take we'll fill our burette with the titrant. Our titrant in this case is the standard EDTA solution, that is 0.01 molarity. And then you measure 50 milliliters of the sample water to be tested using the measuring cylinder, pour 50 ml into the conical flask with the stirrer. So the magnetic stirrer, once placed on the magnetic stand, does the stirring once it is switched on. So it keeps stirring the sample water, so you don't need to shake the sample before pouring it into the conical flask. And then you add 1 milliliter buffer solution followed by 1 spatula full of indicator. And then you will titrate your sample against our titrant, in this case, standard EDTA solution. And then until a color change is observed, that is from wine red to blue, and then you will take your final burette reading. And then the results are obtained using the formula that is used. Next slide. Yeah, so after a color change from wine red to blue is observed, you will get the titer value, that is the final burette reading. You subtract that with the initial burette reading. That will be the volume of acid used, and then you will multiply that with 20 to get results in the following unit, that is milligram per liter of calcium and magnesium ions. And then as usual, the results you get, you will interpret them using your country's standards for drinking water, who recommends a standard a maximum of 500 milligrams per liter calcium ions and magnesium ions in drinking water. Next, we'll tackle calcium ion next. So apparatus to be used will remain the same. The reagents we'll use this time will be sodium hydroxide, sodium hydroxide, urexide indicator, and standard EDTA titrant. The procedure, next slide. The procedure, as usual, we start with rinsing our apparatus and then measuring out 50 ml of the sample and pouring that into the conical flask, and then we'll add 1 ml of sodium hydroxide solution, and then 1 spatula full of urexide indicator, and then a color change to wine red will be observed. And then the sample will be titrated against our standard EDTA titrant until a color change to violet is observed, and then the final burette reading will be taken. As usual, you will take the final burette reading and the initial burette reading, find the difference. The difference will be your titer value or the volume of acid used. You multiply that by 20 and you'll get your value. That will be the calcium ion value in water, and it is measured in milligrams per liter of calcium ions. Who recommends a maximum of 100 milligrams per liter of calcium ions in your drinking water? Next, fluoride. So fluoride is a mineral that occurs naturally and is released from rocks into soil, water, and air. Fluoride in water to a certain level is beneficial to humans, but causes dental and skeletal fluorosis if the levels exceed a certain recommended amount. In this case, who recommends a maximum of 1.5 milligrams per liter of fluoride in water? Areas within the Rift Valley, that is certain areas in Kenya, basically where the Rift Valley passes through, the areas are very high, have very, the water in those areas have very high fluoride levels. They say there's a lake here in Kenya, it's called Lake Nakuru. It's famous for flamingo. It's famous for flamingos. I think they say its fluoride levels goes as high as, I think, is it 2,500? I'm not sure. But generally, the areas within the Rift Valley have very high fluoride levels, and it's because of the rocks within that region. So it's important to have a bit of fluoride. That's why fluoride is added into your toothpaste. But if you consume too much fluoride, you will get you will get brown teeth. I am sure you have seen people with brown teeth before. And aside from that, it could also lead to brain damages, and it also causes bow-leggedness in especially children who consume water with very high fluoride levels. So for this parameter, we'll use the photometric analysis from the word for, that is photometric from the word photo. So basically, you will be passing light of a certain wavelength through your water sample to get that. And if the next slide. The next slide on the left, you'll have your you can have an instrument to measure the fluoride levels directly, and then on the right you will have your photometer. With this one, you will have your water sample and then have light pass through it. But the equipment on your right, on your left, just measures the fluoride levels directly. So slide before. So the photometric analysis technique is used to test this parameter. Apparatus to be used will include a photometer, that is the image you just saw on the right. A cuvette, is basically a tube. Yeah, on the right, yeah, that black thing there is a cuvette. A cuvette and a crushing rod. A crushing rod is just a rod to crush the tablets that you'll be using. Initial slide. Yeah, so for this one, we'll be using fluoride number 1 tablet and a fluoride number 2 tablet. And then the procedure for that is as follows. As usual, you will take the cuvette and rinse it 3 times with distilled water, and then fill it to the 10 ml mark. Just as with the turbidity testing, the cuvette is marked to the 10 ml mark, and then you're supposed to fill the cuvette with the water sample to be tested. And then this is after shaking. As usual, if this parameter doesn't use the if this parameter doesn't use the volumetric analysis, that is the one that uses the stirrer, you will need to shake your sample. I forgot to add that with free CO2, you're not supposed to shake your sample because you will be letting the CO2 outside of your water. So you're supposed to use the water as it is. So with this one, you're supposed to shake your sample and then put it into the cuvette. And then you'll take your fluoride #1 tablet, add it into the cuvette, and crush it using the crushing rod. A crushing rod is a very small rod just to crush the tablet. The tablet is literally a tablet, so it needs to be crushed to allow for dissolving. And then after crushing it, you're going to stir it to achieve a uniform color and for dissolving. After that, you'll take a fluoride #2 tablet, add it into the cuvette, crush it using a crushing rod, and then the cuvette content is allowed to stand for 5 minutes to allow for a full color development. After that, zeroing is done using 10 ml distilled water in a cuvette. What zeroing is basically ensuring that your photometer is at zero. So what you're going to use, what you're going to do is you're going to take a cuvette and then add distilled water. Distilled water doesn't have any ions or particles in it, so it can be used to ensure that that is 100%, that is maximum light of water is passing through your sample. So if you use distilled water, you're going to achieve 100% T, that is 100% T, that is transmittance of light through your water. So you're going to use 10 ml of distilled water in a cuvette, and then select a wavelength of 570 nanometer on the photometer, and then switch it on, and then there's that button on the photometer. You're going to long press it until you achieve 100% transmittance. That is 100% of light is passing through the cuvette with distilled water, and then the reading is obtained. That is 100% T reading is obtained, and then you're going to switch the distilled water with the sample to be tested. The sample remember the sample has fluoride #1 tablet and fluoride #2 tablet, and it has been allowed to stand for 5 minutes just to allow for full color development. So you're going to switch this with the distilled water. So you're going to push the cuvette with the water sample to be tested into the photometer, and then you're going to get your reading. And then after getting your reading in percentage T, that is percentage transmittance, that is the amount of light that has passed through your sample, you're going to compare it with the fluoride calibration chart, which is provided to determine the fluoride concentration in the sample. As I had said before, we recommend a maximum of 1.5 milligrams per liter of fluoride in drinking water. But different countries recommend different levels. That is depending on the fluoride you come into contact with. Kenya recommends generally less than 1.5. Yeah. So next, iron. We'll look at iron. So iron is one of the Earth's most abundant resource, making up at least 5% of the Earth's crust. Rainwater infiltrates the soil and underlying rocks with iron, bringing about the presence of iron in groundwater. Sources of iron in surface water include industrial waste and metal corrosion. We'll use the photometric method of analysis. Next slide. Apparatus used as with the initial test, that is the fluoride test, will be a photometer, cuvette, and crushing rod. And then the reagent that we'll use here is the ion HR tablet, and we'll just do the same thing as with the fluoride analysis. We'll take our sample, shake it for uniformity, pour 10 ml into the cuvette, that is 10 ml to the mark. Add 1 ion HR tablet into the cuvette, crush it, and then stir it to dissolve, and then allow it to stand for 1 minute for full color development. Remember, for the fluoride analysis, we allowed the cuvette with the water samples to stand for 5 minutes, but this one will allow it to stand for 1 minute. And then, as with the fluoride test, we are going to do zeroing with this one, that is using distilled water to ensure 100% transmittance of light through our sample. But this time, as with the fluoride analysis, we use 570 wavelength. We'll select the same wavelength for the ion test, and then you'll do the zeroing as usual, and then you're going to replace the distilled water with the water sample to be tested, the sample containing the ion HR tablet, and then you're going to get your reading. And as with the fluoride, analysis, you're going to get the reading for this one, and then you compare it with the you're going to consult the ion calibration chart to obtain your ion concentration in the sample in milligrams per liter. Who recommends an ion value of maximum 0.3 milligrams per liter in drinking water? Next slide. Yeah, what you have there is you can have tablets. There's literally very many ways of testing for this. You can have kits that test for just inserting the kit inside your water and getting the value of ion. That is, with advancement in technology, water testing is becoming so much easier. So we might maybe see a move towards maybe more from the cumbersome and tiresome lab testing, and then you just get self test kits that you can use at home. So next, nitrate. So nitrates are a salt of nitrous acid, which can be naturally or artificially found occurring in water. Sources of nitrates in water will include fertilizer through sewage and also runoff water. We'll use the photometric analysis method for this. Apparatus used as usual, we'll have the pipette, a photometer, and a crushing rod. And the reagent that we'll use here is an electrical tablet. Next. The procedure for that is the same. We'll start by our sample, measuring out 10 ml and pouring it into the cuvette to the mark, and then adding. Before the slide before, and then adding an electrical tablet, crushing it and stirring it to allow for dissolving. And then we'll allow the cuvette to stand for 10 minutes for full color development. Set a wavelength, instead of the 570, we'll set a wavelength of 520 nm, that is a nanometer. And then zeroing will be done as with the initial test, and then we'll get the reading. So the reading obtained will be in percentage transmittance. And then we'll consult the nitrate calibration charts to obtain the nitrate concentration of the sample. The value that will be obtained will be the value of nitrogen in the sample. Next. And then the value obtained is then multiplied by 3.3 to obtain the nitrate value in milligrams per liter. The value obtained once you consult the nitrate calibration chart will give you the value of nitrogen, but we want the value of nitrate in the water, so we'll multiply it by 3.3 to obtain the nitrate value in milligrams per liter. Who recommends a maximum of less than 0.1 milligrams per liter of nitrate in water? Next. We'll have heavy metal analysis. So heavy metal analysis check for the presence of harmful levels of metals in water. Common metals present in water include cobalt, aluminum, zinc, barium, mercury, lead, chromium, cadmium, manganese, copper, nickel, arsenic, and thallium. Consumption of water with these is harmful even in very low levels, as these tend to accumulate in the body, leading to poisoning later on. Tests for heavy metal analysis can be conducted using already existing kits. Next, we'll just do the one for arsenic, because with this one we can use kits already established kits to tell you the quantity of the metals in water. So for the arsenic, aqueous arsenic in the form of arsenate and arsenite may result from the application of pesticides, mineral dissolution, or industrial charges. Arsenite is many times more toxic than arsenate. So the Lovibond test kit is used, would be used in this practical. There's literally many other kits that can be used for this, but we'll use assuming you decide to use the Lovibond test kit, this is what we'll do. It involves the colorimetric technique of water quality analysis. Apparatus and reagents used include test strips, color chart, arsenic 1 reagent, arsenic 3 reagent, and 2 reaction bottles with screw caps. Next, the sample is shaken and 60 ml poured into the reaction bottle to the max. So we need reaction bottles practical, and the reaction bottles are marked at the 60 ml. They are marked to 60 ml. So we'll shake our sample and then pour 60 ml into the reaction bottles. And then 2 drops of arsenic 1 reagent are added into the sample and then shaken. Then 1 spoon of arsenic 2 reagent is added, then shaken to achieve dissolution. And then one of the strips is fitted into the screw cap, and then 1 spoon of arsenic 3 added and shaken. And then immediately a cap is fitted, that is the lid of the bottle. The cap is fitted onto the sample bottle and allowed to stand for 20 minutes. After 20 minutes, the cap is opened and the color of the strip compared with the color chart provided with the kit. As with iron and fluoride and nitrate, there's charts that are provided to help you with the interpretation of the results. And then who recommends a maximum value of 0.01 milligrams per liter, that is of arsenic in water. Next slide. Yeah, what you have there is, you can have this Perlin test. Perlin test is another test kit that you can use. So basically this depends on the kind of manufacturer you want to go with when it comes to your analysis. So there's the Lovibond test kit. Perlin test is also another test kit. We also have Aquasol. So it all depends on who the manufacturer you decide to go with. Next slide. We'll test for microbial analysis now. The other, we can have lead and so many other heavy metal analysis, but with this you can just obtain a kit and get direct readings for that. So microbial analysis. The microbiological analysis of water is an accurate and effective way of testing for fecal contamination in water, as well as total coliform that occurs naturally in the environment. So different methods are available for microbial analysis, but I use the Qualilat method because it is what is most common here in Kenya, and it also provides results that are easy to interpret. So we'll use the Qualilat method. For this, 2 enzyme substrates are included in Qualilat. That is a chromogen that reacts to the enzyme found in total coliform. The enzyme is called galactosidase, and a fluorogen that reacts with the enzyme found in E. coli, that is glucuronidase. Next slide. Yeah, so this is not the Qualilat method of analysis, but I will send pictures for that. Next. So one second. So with the microbial analysis, so basically what happens is that you will take about 100 milliliters of water of the sample water to be tested. Okay, first off, when collecting your sample for microbial analysis, it needs to be stored in glass bottle. This glass bottle has to be sterilized. I think the slides got mixed up. I think the slides got mixed up. One second. So the next slide is the one that should follow. Yeah, that one. So so we'll start for this analysis. You need a sealer, that is a quantity sealer. But I was saying about the sampling for microbial analysis. You will need to collect your sample in glass bottles that are really small, and the time period between collection of your sample to the lab should not be a maximum of 6 hours. So if you don't have a cooler to like preserve your water at a temperature of 4 degrees, you should ensure to get to the lab within 6 hours after your sampling procedure. So once you get your water to the lab and you want to test for it, the procedure for that is as follows. You have a sealer. You literally have a sealer, which is used to seal the quantities. The quantities are what you will pour your water sample into quantities and then seal the quantities using the sealer, and then put the quantities with the water sample into an incubator at around 35 degrees. So the procedure for that is as follows. You will warm your sealer for 10 minutes. Pour 100 milliliters of your water sample into the quantity tray, and then an enzyme substrate is then added into the sample in the quantity tray in the fume chamber, because this substrate produces poisonous fumes. So it's better to do it in the fume chamber in the laboratory. So you pour the substrate into the quantity tray in the fume chamber as a precautionary activity, and then after that, you're supposed to shake your quantity tray so that the enzyme substrate can dissolve in the water. And then the quantity tray is allowed to settle to allow the air in the quantity tray to escape. So you put it in an upright position to allow the water to allow air that might have gotten into the water to, come to the top and like go into the atmosphere. Next slide. The quantity tray is then fixed onto the incubation tray, then passed through the sealer for sealing, and then it is placed in an incubator at 35 degrees Celsius for 18 to 24 hours. After the time elapses, yellow, large, and small wells are counted, and then the results obtained after consulting the MPN table. So the MPN table is literally a table that shows the count for coliforms in water. So you have your quantity that you have placed inside an incubator. So after the 18 to 24 hours, you're supposed to count the number of large wells and the number of small wells that are yellow. So this shows the total coliform in water. And then after that, after counting the number of large wells and small wells and consulting the MPN table, you're supposed to take your quantity and put it inside a UV cabinet, and then pass, that is fluoresce blue light through it, through the quantity. Next slide. To be able to tell if your water has that is enterococci, that is E. coli in water. So you're also going to count the number of large wells and small wells that are blue under the blue light. If you have large wells or small wells that are blue, that indicates the presence of fecal coliform. So that means that your water might be contaminated with such bacteria as the bacteria that cause such diseases as cholera, dysentery, that is any waterborne disease. And then you're going to consult the MPN table that is for fecal coliform, and then the results are recorded as MPN per 100 ml. As usual, you're going to compare the results with WHO standards and your country's standards. So WHO recommends a value of less than 3 for total coliform in drinking water and 0 for E. coli. I mean, you can't have water that has bacteria, that has fecal bacteria in it. Next, let's do the next. Yeah, I think that's it. So, any questions? I hope I wasn't so fast this time round.
Okay, so I don't know if there's any question. It's a great presentation. It's a complex materials which we got, and I think maybe some of you have some questions to ask depending on the first session and this second session. So if you have a question, you can maybe raise up your hand and then you ask a question. Any question? Okay, so we have less than 4 minutes, and we have room for questions. If there's any question, please put up your hands. We could see a couple of people.